Welcome back to the next video, everybody. Today we are going to begin to try to set up the derivation of the standard Langlands tunnel theorem from the automorphic version or the full version of Langlands tunnel. The only issue now in what remains, given what we've done so far, is that the true Langlands tunnel theorem actually provides a so-called automorphic cuspidal representation corresponding to the modular form G that we used in the previous video. It doesn't actually give us the modular form G itself. And so we're going to explain over the next couple of videos how to patch this up with some general theory. And so essentially what happens is that a Hecke eigenform G of weight 1, which is what we wanted and what we used in the last video, with a fixed level and character, this generates a collection of irreducible representations. It's a family of pi sub p's for all primes p less than or equal to infinity. So it's all the finite primes p and then one prime, which we'll call infinity, corresponding to the usual Archimedean absolute value. And these are representations of the local groups GL2 of Q sub p. So pi sub p is a local representation, or a representation of the local group GL2 of Q sub p. Okay, and each one of these representations is uniquely determined by information attached to the Hecke eigenform G. So you have a collection here of sort of, let's call them compatible representations of the local groups GL2 of Q sub p. In other words, what you have is an automorphic cuspidal representation pi of the Adel group GL2 of A sub Q, the Adels of Q. Okay, so I'm being a little bit loose here and I'm not defining a lot of my terms. Some of this will come later though. Okay, I'm just trying to set the general groundwork right now. If you replace Q by a number field K and GL2 by GLN in the discussion on the last slide, you can then start to view all kinds of different objects as really just automorphic representations of GLN over a number field. Things like Dirichlet characters mod n, Hecke characters attached to number fields, modular forms, and other things. This is a very unique, new, enlightening perspective to have. Let's make this a little bit more precise by placing it within the context of the Langlands program. Let's look at the Langlands reciprocity conjecture, which from here on out we'll call the LRC. Here's what it says. If rho is an n-dimensional representation of the absolute Galois group G sub k of k, where k is a number field, or more generally of the Weil group W sub k, which we'll define later, there is a corresponding automorphic representation, which we'll call pi of rho, which is a tensor product of local representations pi sub v over all primes v of k. And this is a representation because it's a tensor product of local representations on GLN of QP put together compatibly. We actually just get kind of one single representation on GLN of the Adels of K. Okay, so you can think of this collection of local representations as one big representation on what we call the Adels. And this representation satisfies the property that for almost all primes v of k, the trace of rho Frobenius at v is the trace of something called T sub pi sub v, which is the Langlands class of pi sub v and GLN of c. And moreover, we can say a little bit more. If the starting representation rho was irreducible, then pi of rho is something called cuspidal. So I owe you a lot of definitions still, I realize that. But again, just try to keep the general picture in mind. N-dimensional representations of the Galois group give you automorphic representations of the Adels, okay? And they satisfy a nice trace of image of Frobenius property, like we're used to our representation satisfying. This is the same kind of property that shows up in the Langlands tunnel theorem, okay? So I owe you definitions of like the Weil group, automorphic representation. I might or might not define the Adels. I owe you definitions of like the Langlands class, cuspidal, things like that, okay, but we'll get there. Okay, so what we're going to do, if we specify, is we're going to define all of these ideas. Like I said, I owe you all that. And we're going to look at the proof of this conjecture in the case n equals 2 and rho is solvable, and that'll be next subsection. So after the next couple of videos, I'm going to spend the next couple of videos, though, setting up some general representation theory. Once we've done all that, we will have produced the following with a sketch of its proof. And we'll call this Theorem 3. And here's what it will say. So it's just a specification of the above conjecture. Let K be a number field to each irreducible solvable representation rho from the Weil group W sub K to GL2 of C. There's an automorphic cuspidal representation pi of rho, which is the tensor product over V of pi sub V of GL2 of the Adels of K. such that what we call the central character of pi of rho is just the determinant of rho. Again, I owe you a definition of central character as well. And trace of the local Langlands class at V, T sub pi sub V, is trace of rho sub V of Frobenius sub V for almost every prime V of K. Okay? So we have this. Okay? So we're going to take all this stuff from this video for granted, and we're going to show classical Langlands tunnel. And classical Langlands tunnel is what we used last video to get that the irreducibility of rho bar E3 implied the modularity of rho bar E3. Okay, so let's start the setup now, just a couple of slides, and then we'll continue next video. Let's let G denote GL2 of R. So this is G sub infinity, okay, because it's corresponding to the infinite prime, right? Because R is the completion of Q at the infinite prime, which is the usual Archimedean absolute value. This is a real Lie group whose Lie algebra, like frac GL2, consists of all 2x2 real matrices under the commutator Lie bracket. If you've never seen any Lie theory before, you really just need to imagine Lie groups as groups that are smooth manifolds and kind of everything is compatible and continuous and whatever. And then imagine the Lie algebra of that Lie group as just the tangent space at the identity. So here's your Lie group. Here's the identity, E maybe. Here's the Lie algebra. Okay. Let's let frac G be the complexification of frac GL sub 2, which is a universal object with the following universal property. This is just how I think of the complexification. It's not the actual construction, but I'm going to define it in terms of its universal property. Frac G is a continuous homomorphism of frac GL sub 2 into a specific now complex Lie group, which I will also call frac G, such that every continuous homomorphism of frac GL2 into another complex Lie group factors through G. So I have GL2 into G. If I have any other map from GL2 into another complex Lie group H, this diagram must commute with some unique map here. Okay, that's all I'm saying. The complexification of a real Lie group, if it exists, is of course unique up to unique isomorphism by universal property category theory nonsense. Okay, and it turns out this object does always exist. Okay, so that's one piece of the setup we need. We also need to get a handle on this K, which is K sub infinity, which is O2 of R. This is the real 2x2 group of orthogonal matrices. This turns out to be a maximal compact subgroup of G. Okay, a couple more definitions we'll need. A representation pi of a group G0 is called a unitary if for all G and G0, pi of G is a unitary matrix, meaning the inverse of pi of G is its conjugate transpose. That's just some linear algebra. Okay, another definition we'll need. If V is a completely reducible representation, by definition, we can break it down into a direct sum of irreducible subrepresentations W sub K, each to some multiplicity N sub K. Okay, these are the irreducible components of V. And what we're really after here is what is the definition of an admissible representation of G? Remember, G is GL2 of R on a Hilbert space H. And what that is it's just, of course, a homomorphism pi from G to GL of H as expected. But what does this admissible mean? Well, it means two things. I want the representation to be continuous, just baseline continuous. In other words, I want the action map from G cross H to H, which sends G comma V to pi of GV, to be continuous. But remember, a representation is just the same thing as an action map, essentially. So I'm just saying I want pi to be continuous here. And then what is this admissibility thing? Well, for this specific setup, the Archimedean setup, admissibility means the following. The restriction of pi to K, the maximal compact subgroup of orthogonals, contains each irreducible unitary representation of K with finite multiplicity. And this makes sense as a demand because as a consequence of the Peter-Weyl theorem, every continuous irreducible representation, in other words, each one of these representations here, of a compact group, which is what I have because I'm on K, is finite dimensional. Okay, so that is what in the Archimedean setup, that's what an admissible representation of my G equals GL2 of R is. Let's look at this from another perspective. This is a very helpful perspective to have. Let's say pi from G to odd H is admissible in the above sense. And let's let V equal V sub K and H be the subspace of what we call the K finite vectors, which are those vectors V and H whose translates under pi of K span a finite dimensional space. Now, unfortunately, these vectors are not in general preserved by the action of pi of G. However, they turn out to be preserved by the corresponding action of frac G, the differentiated action. So the action of G admits an action of frac G. So what I'm just saying here is the action of the Lie group admits an action of the Lie algebra. This is standard Lie theory. In fact, if you view V as a representation space simultaneously for both frac G and K, which you can do, V is a so-called GK module. Well, what that means is essentially that V is not just an analytic Lie theoretic object, it's also an algebraic, kind of linear algebraic object, okay? However, even when you think of it as an algebraic linear object, V still contains accurate information about the properties of the original pi. So I know I'm being very naive here, but this is all you really need to keep in mind for now. Here's what I mean. Here's an example. It turns out pi is irreducible in the usual representation theoretic sense, if and only if V is irreducible in the algebraic sense, in that V has no vector subspaces invariant under both pi of k and the differentiated action d pi of frac g. Okay? In fact, more is true though. Like there's an equivalence of categories even between the category of irreducible admissible representations of G and the category of irreducible GK modules. And so all this is really to say that for the rest of the discussion that we're about to have over the next couple of videos, we can conveniently just write V instead of pi if it's convenient to think of pi as its equivalent GK module. And the reason for that is this equivalence of categories and the fact that a lot of the algebraic properties translate to representation theoretic properties. Okay, so we're sort of set up now. We'll look at some examples next time. We'll just keep pushing forward. So I'll see you then, and thanks for watching.